Any questions at all? I mean, I haven't done a lot quite yet, but things are good. All right. Well, let's continue on then with our discussion of systems of linear equations. Talk a little bit more about solving with elimination, and then we'll move into solving using a specific algorithm, or algorithms, I guess I should say. Pardon me. Going forward. So we talked last time about doing elimination with equations and hoping that we could get down to this triangular form that we talked about right at the end, because then we could go use that back substitution process to get the solution or solutions, if necessary, to the system as we're going forward. So as we're going through these elimination things, let's talk about what kind of allowable operations we would have, because we're going to extend these then to our algorithm later on. So one of the things that we did, a couple of things that we did last time, were these two operations where we, say this one here, we multiplied by, I'm supposed to get these out of here and they did not, multiplied one equation by a constant, right? That's basically just multiplying both sides of your equation by a number. There's a number we want to make sure that we don't necessarily multiply by. It might turn a false statement into a true one. What don't you want to multiply both sides of the equation by? 0, right? Because if I multiply both sides by 0, I get 0 equals 0, which is a true statement. It may have been a false statement to start with, right? So we don't want to use 0, but any non-zero constant will be fine. We also did this kind of strange one, if you will. It kind of feels a little bit strange. We multiplied an equation by a constant, added it to a second equation, and then replaced that second equation, right? Okay. So that's another one of the operations that we'll do, and that helps us eliminate one of the variables, if you will. Another one that we'll do is that we could literally just swap two equations around. That's not going to change the system of equations at all. Good morning.
Good morning.
That's not going to change the solutions to the system at all if I just reorder the equations. So those are going to be our three basic operations. Hello. That will do that. It'll yield equivalent systems. So one of them is multiply an equation by a non-zero constant. That's not going to change what the solutions are. We can also just swap two equations. What I mean by that is just basically take two of them and just write them in a different order. Hello. And then the third one, there's that a little bit, I like a little bit stranger, but it's the same idea. That's how what helps us actually eliminate some variables. Notice that the first two operations won't actually eliminate anything, right? The third one actually does the elimination. We multiply one equation by a constant. In this one, well, it'll be a non-zero constant, otherwise we're not going to actually do anything. Multiply one equation by a constant, add to a second equation, and replace the second equation with the result. The important thing to remember with this one is that the first equation doesn't actually change. I shouldn't say the first equation. I should say the one we'll call this the one that we're multiplying the constant by doesn't actually change. We're doing that multiplication kind of as an intermediate step, but we're leaving it unchanged. If you're going to think about it a different way, you could multiply by the constant that you need, then add, and then just undo the multiplication by the constant by dividing by it. All right, so these are the three operations that yield equivalent systems for us. We want all three of these because our idea here is to try to get our systems into this triangular notion, right? Because when we have this triangular notion, we're able to use this back substitution process to give us a solution, or solutions if we have more than one. Okay. Also notice that in this particular case, notice that the coefficient on the x, on the y, and on the z here, those leading ones, the leading variables that we have in each of the equations are also a 1, so we didn't have to do any division at the end, right? It's also, if we're doing elimination, it's a lot easier to figure out what you need to multiply by if you have a coefficient of 1 to start with on one of your variables. Going back up to the example we did last time. No, not that one. Sorry, this one. Notice in this case, when we went to eliminate this 3x1, we worked off of this x1. It was easy to figure out what constant we needed because we just needed to do the opposite of whatever's on this one. Right? So that's going to kind of be our process going forward. Is we're going to try to get a coefficient of a 1, then eliminate the variables that are associated with that, then get a coefficient of 1, and just keep repeating that process. And that's the algorithm we're going to use later on. Okay? So let's go through this with an example. So we're going to use elimination to write this system in a triangular form, and then use back substitution to find our answers. So we've got x plus y plus z equals 2 is the first equation, negative x plus 3y plus 2z equals 8 in the second equation, 4x plus y equals 4 in the third equation. So again, our first step would be get a 1 coefficient up here in that whatever order we have for our variables. Usually we think about alphabetical, right? So in this case, we have x, y, z. I want a 1 as our coefficient as leftmost as possible as we can get in that first equation. Now, if these two had x's in them and this one didn't, we'd want to swap first to be able to do that, right? If this were just a y plus z, say, and I want to try to eliminate x's, I'd want to swap one of those up to the top to be able to get that triangular form that we're talking about. Okay. We'll see more examples of that as we go along. Notice in this case, we already have a 1 here, so there's not a lot to do. So if I want to get rid of, say, this negative x, what would you need to do? Good, yep, add equation 1 to equation 2, and replace that equation 2. No, again, that's not going to change the first one. As you add down, the x's go away. Y plus 3y gives you 4y. Z plus 2z gives you 3z. And the 2 plus the 8 gives you the 10. Now, we will do the next one as well. Usually we'll do, if we're trying to eliminate one of the variables, usually we'll just do them all at once and not write one, do one and write a whole new system and then do another one and write a whole new system because it's going to take up a lot of paper to do it that way, right? So let's go ahead and get rid of this 4x. Stupid things. They're supposed to get these out of here, and of course I don't pay attention to where I'm walking and then I run into them. All right. So again, when we're trying to eliminate these two, I always want to work off this thing that's in the upper left-hand corner. Okay. So working off of this, what do I need to do to this equation to get rid of that 4x down here? Yeah, multiply by negative 4 and then add, right? So we'll do negative 4 times equation 1. Add it to equation 3 and replace equation 3. What do we get when we do that?
Negative 4x plus 4 plus negative 4y plus negative 4z equals negative 8.
Okay, so that's what's going to be that first equation, right? I'll get a negative 4x minus 4y minus 4z equals negative 8. And then when we add down, what do we end up with? Good. So we'll have negative 4y plus the y gives us negative 3y. Negative 4z plus 0 gives us the negative 4z. Negative 8 plus 4 gives us negative 4. Yeah. So far, so good? All right. All right. So then the next step, if we want to try to get this in that triangular form, oops, and again, trying to get coefficients of 1, I need to make this a 1, right? If I can. Now, there's a couple of ways to do that. Maybe the most straightforward way to do that is to just divide by whatever coefficient you have there, right? Multiply by a 4th. But if you're clever and don't like fractions, there might be another way that you can see to get a 1. Can you see how to combine one equation with another one and get a 1y up there in the second equation without having to use a fraction? What can you do? Yeah, add the third equation up to the second one, right? About a 4 and a minus 3. So you can be a little bit clever when you're doing these as long as you're doing those allowed operations. We can do equation 3 plus equation 2 and replace equation 2. Obviously, that doesn't change the first equation because we're not doing anything with the first equation, right? And again, since we're replacing equation 2, we're not changing equation 3 at all. What does the second equation become? Okay, so you get a y minus z equals 6. We're adding up in this case, right? Everybody see that? Okay. Now, again, so notice the process here, and this is going to be very repetitive. This is what we're going to do later on as well when we formalize our algorithm we're doing. Notice the process. We got a 1 here for a coefficient, and then literally we got 0 coefficients here and eliminated those, right? Then we worked on the second equation. What do? We got a 1 here. What do we want to do next? Get a 0 here, right? I want to make this one go away. So what do I need to do to this equation? Or what do I need to multiply this equation by to make this go away? 3, right? So we'll do 3 equation 2 plus equation 3, replace equation 3. Again, doesn't change the first equation. Pardon me. Doesn't change the second equation, because remember that multiplication by 3 is just that intermediate step. What do you get when you then do 3 equation 2 plus equation 3 and replace equation 3? What do you end up with? Okay. Okay. 3y minus 3y gives you 0. Negative 3y negative 3z minus 4z gives you negative 7z. 18 minus 4 gives you 14. That okay? All right. Last step now to put it in that triangular form. And again, when we say that we're putting it in the triangular form, we mean we want 1 for the coefficients on all your variables as you're going down and to the right. What do we need to do for our last step to put it in that triangular form? Yeah, divide by negative 7, right? Do negative 1/7 of equation 3 and replace equation 3. That just changes the last equation then to z equals negative 2. That okay? All right, so now we're ready. Once we've got it in this form, notice we've got 1s kind of down this diagonal idea, right? And we've run out of equations. I can't do anything else. Now we're ready for that back substitution step because this literally tells us what the z is, right? Once we know the z, can we figure out the y? Yep, and then once we know y and z, can we figure out the x? Yeah, so that's that back substitution process. So when you do your back substitution, whoops, y minus negative 2 equals 6, so your y will be 4. Yeah. And then your x plus 4 minus 2, so 4, equals 2, and so your x looks like it's 0. So if we write our solution then, what are you doing? Stop it. Our x, y, z will be 0, 4, negative 2. And you can always check your answer, right? Because that, if you plug in 0 for x, 4 for y, negative 2 for z, into each of the 3 equations, you should get true statements. So you can always check your answer when you're done. Questions? Let me ask you this question, because this is where we're going to go when we go to the next section here. Did the letters matter? No, all we kept track of was really the coefficients, right? That was the important thing, right? The letters, I could have changed the names of the letters. We didn't do anything with the letters, really, right? So it was really more the numbers. All right. So let's look at the next example. Got x1 plus 4x3 equals 13. 4x1 minus 2x2 plus x3 equals 7. 2x1 minus 2x2 minus 7x3 equals negative 19. All right, so again, we're trying to be very algorithmic about this, right? Get a 1 for your coefficient as left as most as you can in the first equation, then get 0 coefficients below that. Leave that first equation alone because we're trying to just worry about getting that triangular form, right? Do the exact same thing for the second variable. Do the exact same thing for the third variable as you're working down. Okay. Do I need to do anything to this x1 to start with? No. Okay. So let's get rid of the x1s below it. What do we need to do to get rid of the x1s below it? Stop it. X1 plus so anytime we're trying to get rid of these, well, I want to work off that one that we have a 1 on. Anytime I want to get the eliminate the ones below it, I always want to work up to the top one that I can. So what do I need to do to get rid of that 4x1? You multiply E1 by negative 4 and add it to E2 and replace E2, right? What do I need to do to get rid of the 2x1? Multiply by negative 2, right? So what do you get for your second equation when you do that operation?
Negative 2x2 minus 15x3 negative 45.
Okay. So going through each one of them, negative 4 times the x. I really can't pay attention to my surroundings. We have to change. Okay. Negative 4 times the x1 plus then 4x1 gives you 0. There isn't an x2 here, so 0 minus a 2 gives me negative 2x2. Negative 16 plus 1 gives you negative 15x3. Negative 52 plus 7 gives you negative 45. What did you get for the third equation? You get the exact same thing? Yeah. Okay. So going through it again, negative 2 plus 2 will give you 0. There isn't an x2, so it still has a negative 2x2. Negative 8 minus 7 gives you negative 15x3. Negative 26 minus 19 gives you negative 45. So far, so good? All right. Now, you get the exact same thing. So if we're going to eliminate, something's going to happen. But let's go ahead and just keep doing the process. Our next step in the process would be make this a, what do we want this coefficient to be? 1, right? I can't really do the same trick we did last time of manipulating this one so that I add them and get a 1. So again, more straightforward way to do it is just to divide that by that coefficient, right? I subtract what?
Like E1 to E2 to E3.
Will that be a 1 there though? If I subtract them?
Oh.
Okay, yeah. So I'm just trying to go through the kind of the process we're doing because eventually we're going to switch this over and not do it by hand and use the calculator. And the calculator is going to do it the same way every single time. So I just want to make sure we all understand what the calculator is doing essentially. Okay. Or the computer. All right. So I still have the same first equation. Oops. The second equation now becomes x2 plus 15 halves x3 equals 45 halves. And I didn't change the third one. And now the next step is to get what? Now that I got a 1 here, I want to get a 0 here, right? And then what do we need to do to get the 0 here? I want to make this a 0 now. Yep, good. Yeah, take 2e2 plus e3 and replace e3. And what happens then when you do that? Yeah, you get 0 equals 0, don't we? This is now triangular. We've just eliminated the entire third equation, right? Essentially, what this is telling me is that the third equation is not giving me any new information, right? Now, is this a true statement or a false statement? It's a true statement, right? So we're still okay. If that had turned out to be a false statement, you would have told me what for the system? No solution. Good, yeah. When we have no solution, we refer to that as an inconsistent system. Inconsistent means no solution. So you'll hear that word quite often. But this is still consistent. But now we're out of information. If you've had Calc 3, essentially what you've got is maybe you've got 2 planes that have intersected in a line. And then you've got a third plane, but it goes through the exact same line. Okay? Think about if you think about a book, for example, and just pretend like this is one single line, all your pages meet in that same line, right? So if you have 2 pages that intersect and give you a line, a new page isn't going to give you a different line. It's all going through the spine of the book, right? So that's essentially what this is doing. You've got 2 planes. The third one goes through the exact same line of intersection. Yeah.
How did the 13 become negative? And then also, how did the...
Oh, I just wrote down the wrong number.
Also,
Yep. You're right. It shouldn't be negative.
is there supposed to be 2x3's in the third equation?
Oh, that's just a typo. That should be a 2. Thank you. Okay. All right. So this is just telling me that I've got 2 planes, essentially, that gave me the information of where they intersect. The third one didn't give me any new information. So now when we're writing out the answers to this system, I need to write out the answers that refer to an entire line. And that's when we're going to use that parametric form again. Okay? So this variable here, this x3, I can pick whatever I want for it. But once I've picked whatever I want, I can solve for the x2 and the x1 using that back substitution idea, right? So we'll say x3 is t. What's your x2 going to be if you put in t for x3? Using this equation here. If I put t in for x3 and solve for x2, what do you end up with?
45
Good. Exactly. And then you do the same thing for the x1. Careful.
13 minus 45 over 2 minus 15. What? I'm lost.
I'm putting t in here, right?
Oh, 13 minus.
There we go. 13 minus 4t, right? Yeah. There wasn't an x2 to plug anything in, correct? We took the t, put it in right here, and then subtracted to solve for your x1. Yeah, it's up here. So those are our answers for that. And again, if we want to put this as an ordered pair, which you might be asked to do in WebAssign. Yeah.
You say, so if it's 0 equals 0, you put in a variable?
The 0 equals 0 part is just telling you that there's not any information that that equation gives us. Okay? So I look back here, I'm done, right? I've got more variables than I have equations. So that's when that's what it's going to tell me that I need to put something in for one of the variables as a parameter. And then once I know what that parameter is, I can solve for the other ones. So again, if I write this as an ordered triple, we'll just put those individual pieces in each of those spots. What other questions do you have on that one? Right. So obviously, at least I hope it's obvious, that this can kind of suck when you start getting bigger numbers or nasty fractions or those kinds of things. So I probably want to use some technology to help us do these different things. So we've got a couple of different options that we can do. Well, if we want to actually type in the equations, we probably want to go to a computer, what's referred to as a computer algebra system to help us. One of the nicer ones that you can find is online called GeoGebra. So we'll write down the website up here. If you're doing homework, you might want to use this particular site. I'm going to show you lots of different, well, not lots, a few different ones. This one, you want to go to the classic interface. So geogebra.org/classic is the website. When it loads up, it'll give you an option here for lots of different things. Most of the time, if we're going to use GeoGebra, we're going to want to use the computer algebra system, the CAS here. So click on that. It'll switch this window slightly. I don't care about the graphics window, so I'm just going to scooch it out of the way. The command for solving an equation or solving a system of equations in GeoGebra is the solve command there. And notice if I just click on that menu, it gives you lots of different options. The nice thing about this is that you can see the different types of syntax that you can use for those functions. What we want to do is solving a system of equations. So I want to use this one that says list of equations, comma, list of variables. And what it'll do, if I just highlight that and click on it, it'll actually put in list of equations kind of grayed out for you. Let's see if I can zoom in a little bit. Better? Okay. It's grayed out a little bit here. When you want to type a list in GeoGebra, you use braces. Pardon me. Sorry. And now I'll just type in the different equations that I have with the variables in them, just inside the braces, and I'll separate them by commas. So the first equation is 120.2x. The second equation is 62.4y. The third equation is 36.5z, and that was equal to 258.64. Okay. Do the same thing for the second equation. Well, I'm going to show you how we're going to change this over where we can put your calculator as well. I just wanted to show you GeoGebra to give an introduction to it, to show that it'll deal with variables as well. Oops, forgot my equals. And then finally, the last one was 88.1x plus 72.5y minus 28.5z equals 225.88. All right, so again, type your equations inside the braces, each of them separated by a comma is the syntax. Do the exact same thing for your list of variables. To make a list, put the braces, x comma y comma z. Those are the variables that we have.
Yeah.
Okay. Hit enter.
X comma. Oh.
Yeah. Hit enter. It'll solve it for you. Notice in this case it changed the decimals over to fractions even for you. So it gives you the solution pretty quickly, which is a lot better than trying to do all that by hand, isn't it? Yeah. Okay. I'm going to expect you to do these operations by hand, but eventually we want to use these things to help us do other types of problems. So I don't want you to spend 30 minutes trying to do this elimination process for every single problem you're ever going to do. Okay. So I wanted to use this one as an excuse to show you what GeoGebra looked like in particular, because it'll deal with the variables as well. Your calculators won't deal with the variables unless you've got a computer algebra system on your calculator. Now you could still solve this on your calculator as well, and we'll talk about how to do that later. But you wouldn't type the variables in with it. This okay? All right. Last thing I want to mention before we go on to some new stuff here is, what do we mean by a homogeneous system? Notice that a homogeneous system here, what it means to be homogeneous is that all of your constants on the right-hand side are 0. That's what homogeneous means. Okay, so whenever you have a homogeneous system, what we mean by that is every single constant on the right-hand side of the equation is 0. If even one of them is something other than a 0, it's not homogeneous. Okay? Has to be 0. What are you guaranteed to have as a solution? For any homogeneous system, what has to be a solution? 0. Yeah, 0 is the origin, right? When you put 0 in for all the variables, you get a true statement, don't you? Yeah. So absolutely every single homogeneous system is consistent. Okay? The reason why it's consistent is because we can use zeros for the values of the variables. To get a solution. They're always consistent. We refer to this as the trivial solution. What we will be interested in going forward is whether or not the homogeneous system has non-trivial solutions. Are there solutions that aren't just 0? Okay. If you're in differential equations this semester, or you've had differential equations, you're you'll a lot of times look for solutions to the homogeneous equation, which is you want non-trivial solutions for, in the homogeneous equation for differential equations. They give you a piece of the information if you have something that's not homogeneous. Anyway, what we're typically interested in if we're dealing with homogeneous systems is, does it have non-trivial solutions? So let me just pop back over to GeoGebra real quick rather than going through all the arithmetic to solve this one. And let's see if it has non-trivial solutions or not. And then we'll talk about what that looks like later when we use our calculator to help us out. So if I flip back over to GeoGebra real quick and use our solve command again, the equations here were 2x plus 3y equals 0. Oops. I can type 2x plus 3y equals 0. I have 4x plus 3y minus z equals 0. And I have 8x plus 3y plus 3z equals 0. And the variables were again x, y, z. I get 0, 0, 0. So I only get the trivial solution in this case. If we would have had non-trivial solutions, this would have written, say, x and y in terms of z, or maybe x in terms of both y and z. And we'll see more of this later, like I said. The big deal about this is what I wanted to mention is that homogeneous systems always have the trivial solution. When we deal with homogeneous systems, we're going to hopefully find non-trivial solutions. That's what the applications are going to be later on. Questions on that at all? Mm-hmm.
So, when it's a homogeneous system,
Mm-hmm.
the solution to x, y, and z is so easy.
That always is a solution, but we might get more. It's possible we could get more. Okay. For example, over here in this equation, in this one, if we would have had zeros for our constants rather than what I had there, then we would have had the exact same types of solutions. We just these constants would have been gone. If this had been 0, 0, 0 on the right-hand side, notice that we would have done the exact same thing to get to our reduced form here, but these would be zeros, and so we would get infinitely many solutions in that case. Okay. We just wouldn't have these constants on the end. Okay. So we would have infinitely many. So all we're saying is that zeros always work, but we might get more. We have to do more. We have to do more investigation to see if there's more than one solution or not. You should always solve it. Yeah. Yep. Okay. All right. So let's move on to the next section here. We already noticed that really when we're doing all of this stuff, all we're really doing is keeping track of what the coefficients are, right? So that's what we're going to do in this section is talk about, well, let's just keep track of the coefficients and then interpret the answer when we're done. We'll start that today and we'll finish it up on Monday. So section 1.2 talks about Gaussian elimination and Gauss-Jordan elimination. Before we get to that, we need to have a discussion about how we convert our systems of equations over to a matrix form. Scroll over and scroll up. Doesn't like it when I go fast. Okay. All right. So that's what our first definition here is. A matrix is just a rectangular array of numbers. That's all we mean by a matrix. There's lots of different ways to make rectangular arrays. Maybe you have some square array like this, but they don't have to be square. Maybe you have something like a vertical column. That's a rectangular array of numbers. Maybe you have something elongated this way. Those are all examples of matrices. Now, by convention, we usually will use a capital letter to denote a matrix. Okay? So maybe this is my matrix, say A here. Maybe this is my matrix, I'll call it C here. Now, the one exception to using a capital letter to denote a matrix would be if you have, in this case, one column of things, or maybe you have one row of things. If you've dealt with vectors before, this should look like a vector, right? A lot of times when you deal with vectors, you use a boldface letter, or boldface small letter, and we still do that in linear algebra as well. Of course, it's harder to write in boldface. So when we write, rather than writing something with boldface, we put a little arrow over the top. And I'm super lazy. I don't like finishing off my arrow. So I just go and then put the little top half of my arrow and not put the bottom half of my head of my arrow on there. Okay. This is the one exception when you have something that's a matrix that you don't use a capital letter for the notation, if it looks like a vector. In this case, we would refer to this as a column vector. If you had one row, you might call it a row vector. We will deal with row vectors and column vectors later in the semester. All right. So that's what we mean by a matrix. Every number in that matrix is referred to as an entry. Okay. We'll talk about how we identify entries here in a second. But the last part is might want to know what we talk about, how many things are in your matrix or what size the matrix has. We usually refer to that, the size, by the dimension of the matrix. When we refer to, pardon me, when we refer to the dimensions of a matrix, we talk about how many rows and how many columns it has. We always write the number of rows first and then the columns. So this is going to be referred to as an M by N matrix if you have M rows and N columns. So going back up to the examples that I wrote above, what are the dimensions for A? 2 by 2. What about B? Yeah, it's a 3 by 1 because it's always rows by columns. This has one column, so it's a 3 by 1. What about C? 2 by 4. Good. Everybody okay with that? All right. So if we want to identify a particular entry in a matrix, well, entries are typically referred to with little letters, and the small letter will correspond to the capital letter in the matrix. Okay? So if my matrix, I'm talking about capital A, I would use a little a and then do two subscripts. The first subscript is the row number. The second subscript is the column number. If you're familiar with Excel, that's not what Excel does, right? If you want to refer to a cell in Excel, it's column then row, isn't it? Okay. That's not what we do in, well, anywhere else besides Excel, typically. Okay? Is row then column. All right, so if I go to this example here, what is the 3-1, sorry, not 3-1, 1-3 entry? 2, yeah, it's right here, right? That's the 1-3 entry, row 1, column 3. If I want A sub 2, 5, that would be 11. Yeah. Now, if I wrote down 3-1 to start one with, There isn't one there, so that's just undefined, right? The A is a 2x5 matrix. Okay. Likewise, if we look at this next matrix here, pardon me. What are the dimensions of B? Good, yeah, 4x3, good. So if we want to identify a couple of different entries, what about B sub 4-2? Good. Everybody see where that's coming from, the 4? Is that one right there? Or B sub 2-3? -2, good. Are we all okay for identifying where these things are? Not too bad? All right. So the whole point of this, and we'll start playing around with these more next time as well, but the whole point of being able to do this is to be able to pick out the pieces of a system of equations that we really want to keep track of when we're solving. We already said that really we only need to keep track of what? The coefficients, right? And play with the coefficients. Because the variables, well, aren't really what we're dealing with. It's just the coefficients. So for every system of linear equations, we can create what's referred to as an augmented matrix in the following way. The first thing that you want to make sure that you have is that your system of equations is written in standard form. Okay? Notice that this one's in that standard form, right? We've got the x's first, then the y's, then the equal sign, and then the 5 and the -2 on the right-hand side. That's in standard form. Is the second one here in standard form? No. So when we get to this example, the first thing we're going to want to do is convert this to standard form before we try to write the augmented matrix. Okay? But here's how you write it. You want to just make sure that you're consistent when you write them down, okay? All right, so as I go from left to right, I want to make sure my variables are in order, whatever order I pick. Typically we go alphabetical, but it doesn't have to be alphabetical as long as you're consistent from equation to equation. However, the constants that you want should always be on the rightmost column, okay? To denote where the equal sign is, we'll put a vertical bar. Now that won't appear in your calculator clearly, but you'll need to remember that there's a vertical bar there when you're doing your augmented matrices. And then you just write your coefficients in. Notice that all my x's are going in the first column, all my y's are going in the second column, and my constants are in the last one. That second example, like I said, that's not in standard form, right? So I need to move all my variables to one side. So, and my constants to the other. So the first thing I would need to do, in the first equation, I need to subtract your 6y and add the 7. In the second one, I need to split up that fraction, don't I? And then move the x over. So you'd end up with -1/5 x minus 3y equals -2/5. And then I can do my augmented matrix. Does that make sense? This part right here is x over 5 minus 2 over 5. And so then I subtracted the x over 5 over. I have to split it up over that denominator. That's how I got the second one. Let's look at this third one. Is it in standard form already? Yeah, okay. What size is your augmented matrix going to have? How many rows and how many columns? 3 by 4, right? Row for each equation, column for each variable, plus 1 for the constant, right? So it'll be a 3 by 4. What's your first row going to be? Yeah, 1, negative 1, 2, 4. Second row will be
7, 0.
good. Notice the Z is missing, so we need to put a 0 in for that. The last one's going to be good. Fantastic. That's exactly right. All right. So that's how we get an augmented matrix out of a system. You should also be able to work backward, which is what the last couple of examples are there. So think about those for Monday. Okay? All right. Other than that, have a good weekend. I'll see you Monday. We'll finish this off on Monday as well. I think everybody got into WebAssign. Yes? Yep.
Okay, cool.
All right. We'll see you later.